Students, now we are going to see what is a paramagnet or what is paramagnetic substance. Now, there are elements or there are substances in which the atoms possess individual dipole moment. Now, when such atoms are placed in an external field, they will get magnetized. In the absence of an external field, what happens is that the dipole moment of the atoms will be in different directions. The magnetic dipole moment will be in different directions. Okay, and hence the net magnetic moment of the atom will be equal to, net magnetic moment of the substance will be equal to 0. Now, when such a substance is placed in an external field, what happens is that, suppose I am applying field in this direction, then the dipoles, the magnetic dipoles, will align itself in the direction of the field, and hence it will have a net dipole moment in the direction of external field. So, paramagnetic substances are those which develop a feeble magnetization in the direction of the magnetizing field. This property is exhibited by materials like magnesia, aluminum, chromium, platinum, etc. Now, the atoms or the molecules of paramagnetic materials possess a permanent magnetic moment, which are randomly oriented in the absence of an external field, and hence what happens? It does not have any net magnetization. Now, when such materials are placed in an external field, what will happen to it? All the magnetic dipoles will align in the direction of the field, and at the end they will be having a net magnetic moment, or they will get magnetized. But I told you diamagnetic materials, they are independent of temperature, whereas in paramagnetism, this paramagnetic property depends on temperature. So, well, at low temperature, temperature should be very low. At low temperature, when very strong magnetic field is applied, the atomic dipoles align in the direction of the magnetic field, producing a net weak dipole moment. And at very high magnetic field, this magnetization approaches a saturation value, which means there is a limit to which the material can be magnetized. You take the paramagnetic material, you keep it inside a solenoid having field, you increase the field strength automatically. Depending upon the field strength, the dipoles of the paramagnetic material will start to align in the direction of field. But there is a limit to the alignment. After a certain value of the external field, there won't be any more magnetization. Okay, and this happens at very high field and low temperature. So, temperature is a very important factor when you take paramagnetism into account. And this can be explained, the dependence of external paramagnetic properties on the external field and temperature is explained using Curie's law. Okay, now if you draw a graph relating magnetization M and intensity of magnetization with temperature, for temperature, you will get a graph like this. Now, what happens? As my external field is increasing, magnetization also, magnetic dipoles getting aligned to the field also increases. But after a certain value of external field, there won't be any more magnetization, which means this is the maximum magnetization. This value is the maximum magnetization which can be obtained in that particular material, and this particular region is known as the saturation region. Beyond that particular region, the material won't get magnetized more. Okay, so the intensity of magnetization M of a paramagnetic material is found to be directly proportional to the magnetizing field H. What does the magnetizing field do? It will align the atomic dipole or magnetic dipole in the direction of field, and it is inversely proportional to the absolute temperature. Why? Because as temperature increases, the atoms are getting energy. So, as a result, they tend to oppose the alignment of the atomic moment, atomic dipoles. Okay, we can write M proportional to H by T, or to change the proportionality sign into equal. What we do, we introduce a constant. Well, C is the constant and is known as the Curie's constant. So, we can write M is equal to CH by T, or I am bringing the H to the side, we can write M by H is equal to C by T, or M by H is what? It is the susceptibility. So chi M is equal to C divided by T, and this is the Curie's law. Okay, now the above relation is called the Curie's law. The law states that far from saturation, the susceptibility of a paramagnetic material is inversely proportional to the absolute temperature, which means as temperature increases, the paramagnetic property will start to decrease and will become a normal material. Now let us see what are the properties of a paramagnet when it is placed in an external field. I told you, when you are placing a paramagnetic material in external field, what happens? There is a net magnetization in the direction of field. So when you are placing a paramagnetic material in an external field, the magnets will get attracted. So they are feebly attracted by the external magnets. Second one, the lines of force or the magnetic field lines prefer to pass through a paramagnetic material than through the surrounding, unlike diamagnets. What does a diamagnet do? The diamagnets will repel the field lines. So the field lines will be passing through the surroundings. Whereas if I am placing a paramagnetic material in an external field, then the field lines will pass through it. Which means the lines of force get concentrated more inside the material. Now, if I am keeping my paramagnetic material in a non-uniform field, definitely it is attracted by the external field. So, it will slowly move from a region of weaker field to a region of stronger part. And a freely suspended paramagnetic material aligns itself parallel to the magnetizing field. If I have a magnetizing external field, and if I am suspending a paramagnetic material, what happens? The paramagnetic material will align in the field direction. Unlike diamagnets, what do they do? They align a direction perpendicular to the external field due to its repulsive nature. And hence, we can say the relative permeability is slightly greater than 1. Why? Because the field lines are passing through the paramagnetic material, we can say the relative permeability is slightly greater than 1, and the material is also accepting the field. So, the susceptibility is a small value because it is a feeble magnet. So, susceptibility is a small and a positive value. But the main thing which you have to consider is their susceptibility varies inversely with temperature as given by the Curie's law. As temperature increases, the paramagnetic property will, the dipole will start to align in different directions or in random directions, and hence there won't be any net magnetization. Okay. Next, we are going to see what is ferromagnetism or what are ferromagnetic materials. Now, a scientist named Weiss, spelling is W-E-I-S-S, but it is pronounced as Weiss. He's a German scientist. Okay, a scientist named Weiss, using his domain theory, explained what is ferromagnetism. So, what is a domain? He explained with the help of a domain theory. Now, like paramagnetic materials, in the ferromagnetic materials, the individual atoms will have a magnetic dipole moment, and the nearby atoms they will interact with each other, and nearly 10 raised to 10 or 11 atoms will have a magnetic dipole moment in the same direction. Now, those regions in which the magnetic moment are in same direction, that region is what we call a domain, and the thickness of domain for a substance is approximately 1 millimeter. So, if I take a ferromagnetic material, in the absence of the field, there will be many domains. There will be regions where the magnetic moments will be aligned in same direction, but if you take each domain, the magnetic moment will be in opposite direction. So, what happens at the end? They add or they cancel with each other, and net magnetic moment or net magnetization will be equal to 0 in the absence of an external field. Okay, so what I am going to do is I am going to place this ferromagnetic substance to an external field in this direction. Okay. So what happens? Each domain or each dipoles, magnetic dipoles in the domain will try to align itself in the direction of the external field, and at the end there will be a net magnetic moment, or we can say the material is magnetized. Okay. Now, in materials like iron, nickel, cobalt, etc., the individual atoms associated with large magnetic moments. The magnetic moments of neighboring atoms interact with each other and align themselves spontaneously in a common direction over a macroscopic region, and this region is what we call a domain. Now, in the absence of an external field, the domains are randomly oriented or distributed. So, the net magnetic moment is 0 in the absence of an external field. Now, when a ferromagnetic material is placed in an external field, what happens? The domains or the dipoles in the domain align themselves along the direction of the magnetic field, leading to a strong magnetization of material along the field direction, leading to a strong magnetization. Because of this, ferromagnetic substance possesses or they are strongly attracted by external magnets. Or ferromagnets are used to make permanent materials are used to make permanent magnets. But like paramagnetism or paramagnetic substance, ferromagnetism also depends on the temperature. There is a temperature beyond which the dipoles will get randomly oriented, or there will be disintegration of the domains, and each individual dipole will be aligned in different direction like a paramagnet, which means above certain temperature, which is known as a Curie temperature, a ferromagnet becomes a paramagnet. Now, when a ferromagnetic sample is heated, its magnetization decreases due to the increase in randomization of its domain. At very high temperature, the domain structure disintegrates and a ferromagnet becomes a paramagnet. And the temperature at which a ferromagnetic substance becomes paramagnet is called the Curie temperature. So, the Curie's law was modified and we got Curie-Weiss law, that is above Curie point. In paramagnetic phase, the susceptibility varies with temperature as given by chi is equal to C dash divided by T minus Tc. The law states that susceptibility of ferromagnetic substance above its Curie temperature is inversely proportional to the excess of temperature. This is what Curie-Weiss law states. Now let us see what are the properties of a ferromagnet. Now, told ferromagnets are strong magnets, so they will be attracted by the external magnet. We are keeping a ferromagnet in an external magnetic field, then most of the field lines of the external field will pass through the ferromagnet. As a result, it will be having a very high permeability value and also a large and positive susceptibility value. Okay. Ferromagnets, they are strongly attracted by the external magnets. Now, the lines of force or magnetic field lines get highly concentrated in ferromagnetic material. So, that magnetic induction B is equal to what? B0 plus Bm will be very much greater than B0. Next point, when placed in a non-uniform field like paramagnets, a ferromagnetic substance tend to move from a weaker field to a stronger region of the field. When a field is suspended, a rod of ferromagnetic material quickly aligns itself parallel to the magnetic field. The relative permeability of a ferromagnet is large and is of the order of thousands, having very high value. Why? Because most of the external field lines will pass through a ferromagnetic substance, and their susceptibility is large and positive. But the thing is, it is temperature dependent. The property of ferromagnetic material is temperature dependent. It decreases, ferromagnetism decreases with the increase of temperature as given by Curie-Weiss law. Thank you.